So now we have to find the values for a and b in our equation. We've got this general solution, and we're after a and b. And we're given some initial conditions. When t equals 0, x equals 3, and the differential is 2. I have two unknowns, so I need two equations to be able to find those unknowns, simultaneous equations. So I form one equation using this information, when t equals 0, x equals 3, and then I need the differential, so I need to take this and differentiate it, and then when t equals 0, let the differential equal 2, and I form two equations, which will then allow me to find the values of a and b. That's the process. So we're now going to start thinking about using simultaneous equations, which we did ages ago. So let's start. So the first one, when t equals 0, then x equals 3. So 3 equals a e to the 0 plus b e to the 0. Because when t is 0, the power's gone. Anything to the power 0 is 1. So we've got that 3 equals a plus b. So we've got one equation. Two unknowns, one equation. So that's our first equation out of our simultaneous equations. Now we have to differentiate this function. So x equals a e to the 0.56t plus b e to the minus 3.56t. I need to differentiate it. dx by dt equals, well, if you remember back to your exponential functions, the power comes down and multiplies by the number in front, and the rest stays the same. So we get 0.56a e to the 0.56t minus 3.56b e to the minus 3.56t. That's our differential. So now we've got this function that involves the differential. So we use the second condition. When t equals 0, the differential is 2. So we can write that 2 equals 0.56a e to the 0 minus 3.56b e to the 0. Anything to the power 0 is 1, so 2 equals 0.56a minus 3.56b. And that's our second equation. So we've got two equations and two unknowns. Let's bring equation 1 down so it's with it. We've got that 3 equals 8, or and 3 equals a plus b. That was equation 1. So now we need to solve them. Now, there's a couple of ways we can go about doing this, so let's just think about this for a minute. And there is no right way to do it. In any given situation, it might be a different way that's going to work. If you think about these things, they're linear. There's no powers in here, no b squared or anything, so it's linear. One way would be to make a's the same in both of these. So if I were to multiply number 1 by 0.56, I'd have 0.56a, and then I could subtract one from the other and they would go, and I'd have b. That's, if you remember that, that's the elimination process. The more general one and the more powerful one, though, and often works, is take number 1, say for example, and rearrange it a so that it reads something like a equals something. So if I were to, from 1, say a equals 3 minus b, I could have done it the other way around, b equals 3 minus a, but I choose to do it this way. from 1, a equals 3 minus b, and then substitute into the second equation. So wherever you've got a in the second equation, I write 3 minus b. 2 equals 0.56 a, which is 3 minus b. So I'll put that in a bracket, minus 3.56b. So now I've got an equation to solve, but I've only got one unknown, so in theory it's solvable. Multiply out the brackets and find b. So I'll pause this while you just do that. So there's the working. Multiplying out the brackets, we get this. Collecting like terms, we get this for the b's, and then putting b over to the left and taking the numbers over to the right, we get b equals that. So that's b, and then we can substitute b back into, I suggest, the first equation, number 1, to find out what a is. So we can find a now, can't we? And we get that for a, 3.078. So now we can write down our particular solution. X equals a, which is 3.078, e to the 0.56 t minus 0.078 e to the minus 3.56 t, if I remember rightly. And that's our particular solution. So if I plot this function in autograph, we get this function. If we go back to our original problem here and think about our boundary conditions, look, it's saying that when t equals 0, x equals 3 and dx by dt is 2. Now if we look at our graph, and that when x equals 0, we can see that where it cuts is 3. So if I were to zoom in on that bit, it would be 3. And there is a gradient there, and the gradient of that line at that point tells us the speed, and that would be 2. So it's starting off at those initial conditions, and then as time goes by, so really we're only interested in this part of the graph, that's what's happening to it. It's an exponential rise. And looking at the function, looking at this value here, the amplitude of the decay function is much smaller than the exponential rise function, so that's sort of taking over. And so that's why we end up with it actually going away to infinity. It's just rising and rising and rising, because this part of the function is the dominant part of the function. Okay, so we've used the techniques to solve differential equations in these 2 pages here. Just have a look through this again, check you see the steps. Form the auxiliary equation, solve the quadratic equation. What sort of solution have we got? 2 real and different solutions, so it's this form. So I can now write the general solution and then use the initial conditions and form simultaneous equations to find the values of a and b. And then we've got our particular solution, which is down here. So take your time and check through those methods when you get time.